Good morning. I'm Cynthia Figge, and welcome to FiRe 5. I'm privileged to lead off this year's conference in conversation with Janine Benyus. I've been trying to get Janine to this conference for several years, and I believe every year that goes by, her work becomes more important to the world. Janine resides in Montana. She is the renowned mother and father of biomimicry, and I'm pleased to introduce her. She is a biologist, an innovation consultant, the author of 6 books, and most importantly, biomimicry, innovation inspired by nature. Welcome, Janine.
Thank you, Cynthia.
Yeah. So I want to start. Perhaps you could give us a sense for those of us who are new to this whole area of development, what biomimicry is.
In its simplest form, it's just innovation inspired by nature. Mm-hmm. So in its practical form, it's actually inviting nature to the design table. Mm-hmm. So it's a method of seeking solutions in which, if you've got a design challenge like adhesion, mm-hmm. You literally go outside. You go out to the beach, and if you're adhering underwater, you look at how mussels adhere and you look at how barnacles adhere. If you want to adhere without glue, you look at geckos. Mm-hmm. And you find out the design principles, mm-hmm. how these organisms are doing it. And that can be either a blueprint, a physical blueprint, or it can be a recipe, like a mm-hmm. chemical recipe, a process. Yeah. Or it can be an ecosystem strategy. Mm. And then the next step is finding that design principle. You emulate it and actually create a product or a process that works the way life works. Mm. It's different from bioprocessing. It's not, for instance, using bacteria to clean water. That's bio-assisted technology. Hmm. Okay. Biomimicry, and the best way to explain it is through examples. Biomimicry, in that case, would be something that a company called MR3 Systems did, in which they looked at how microbes have a particular specific affinity for certain metals. Mm-hmm. And they mimicked the molecule that the microbe uses to scavenge metals out of water. And then they made a mining operation in a box, basically, in which each filter has an affinity for a different kind of metal. Mm. So that was mimicking the way microbes take metals out of water. Yeah.
How did you come to this? The book was published in 1997. And what led you to this field and really thinking about design in this way?
A long, strange trip. I'm a natural history writer, and I never ever imagined that this would happen. I'd written 5 natural history books, and they were all about plant and animal adaptations to place. Mm. That was the thing I sort of specialized on. Yeah. And so after, 15 years of doing that, I started to ask, is anyone trying to learn from the exquisite technology that I'm reading about day after day? Yeah. And at that point, there were lots of people doing it, but it was very much in small and obscure biological journals. Whereas now you read it in the science press almost every day, somebody's mimicking something.
Yeah, good. So the book has been out for 10 years, and I think we're into obviously a very important time on the planet in terms of really some of the challenges that we face. And so I wanted to talk with you a little bit about your view of how this is beginning to play a part in solving some of the challenges that we have ecologically and socially. I think when you wrote the book, there were tons of really research in play, but as the field has evolved, where do you see, what is going on right now in terms of biomimicry?
It's interesting. It's back in '97, if I would go to the search engines at that time and type in biomimicry, there'd be no hits. Now if you type in biomimicry or biomimetics, it's synonyms. there are 7.5 million hits. You know, it's a really well-known concept now,
Yeah.
I think, especially in the design professions. And the patent database there are people tracking the patent database, and the patents having biomimetic in them is basically a hockey stick. There are centers for bio-inspired design popping up all over the world. So it has moved from the research bench into commercialization.
Yeah.
Definitely.
Yeah.
And it's also what's really new, at least in where we're working in Biomimicry Guild, is that it traditionally had been funded for decades by military. So, you know, mimicking penguins to make a better torpedo kind of thing, or by the space agencies. And now what I'm seeing is that people are willing to give this method a try to solve sustainability challenges.
Great. So we're gonna, Janine and I have been rewarded because we were first up at 8 o'clock
Yeah.
with the privilege of showing a few slides. So a little bit of an exception. We call this the year of the biologist.
Yeah, I'm using the biology exception.
So we're just gonna take you through a couple of the case studies that Janine has been working on, and we're gonna start with material world and materials innovation. And Janine, I'm gonna just let you kind of guide us a little bit as you go.
Okay, let me grab a few of these guys though first in terms of materials. Many people have probably the next Velcro is going to be, I'm sorry, we go back. I was trying to use here we go. Lotus effect, I think, is going to be the next Velcro. Lotus effect is basically, this is a close-up picture of a lotus leaf. And leaves are self-cleaning structures. These nanobumps, waxy nanobumps, cause water to ball up. They also cause dirt particles to sort of teeter on the tips. And as the rain rolls off, it pearls off the dirt. So already there's 12 different product categories for this. You can buy a paint right now. You could have painted this building in lotus and paint, and rainwater would clean the building instead of detergents or sandblasting. There's the building materials that Cynthia talked about. This is a really interesting one because we're using, we think of CO2 as the poison of our time. So we're thinking about ways to take it and sequester it under the ground.
Right.
Whereas large groups of organisms use CO2 as their primary building blocks. So like plants, that's how they make their starches and sugars. And these guys, the mollusks, any organism, I have a bracelet here that has basically seashells and coral on it, and CO2 is the building material for that. The thing is, there's a certain kind of chemistry that these organisms use. CO2 dissolves in seawater, and then calcium and carbonate, they pull those local building materials out of seawater to create the shell, right? And that has finally been mimicked, actually. What we do now when we're making, say, cement, calcium carbonate's the main ingredient for cement. We go to limestone cliffs, we mine them, we pulverize the rock, and what that basically is the dead bodies of seashells. Instead of that, we're borrowing the recipe from mollusks and making limestone out of CO2. Making tons of limestone out of CO2. It's work that was done at New Mexico Tech, and let me show that. And the company's called Co2 Solution. And what it is they've borrowed the recipe and they're using the enzyme that the mollusk uses. And that's a flue scrubber. And what happens is you need to be near seawater for this. You bubble seawater through this device, and the enzyme is attached to the substrate there. And seawater plus CO2 equals bicarbonate that you then turn into limestone. So literally in a concrete factory, you can be sequestering your carbon in the raw material for your cement. And since cement manufacture produces 8% of the CO2 worldwide, that's a big deal.
That's a big deal.
And you can imagine in a city, this is back to the local building materials.
Yeah.
You can use CO2 to create the local building materials. It sounds like so obvious once you hear it, but there was somebody studying how mollusks make their shells a long time ago, and it seemed like that research was irrelevant, and now there's a company. Here's another one, the second one on CO2 as a feedstock. This is Jeff Coates from Cornell. He now has a company called NovaMer. And his insight was that plants are using CO2 all the time to make long-chain polymers. That's what our plastics are. They make them into starches and sugars. But he found a catalyst that speeds the reaction up. It's really, CO2 doesn't want to hook up. But he found a catalyst based on how plants do it, and now he's making biodegradable polycarbonates, like the stuff in CDs and sunglasses. And he's making it out of limonene and CO2. Here's another example. Well, we haven't mimicked this guy yet. That's the flying squirrel for my cabin. But the whale, the humpback whale, those scallops along the edges turn out, they're called tubercles, and they turn out to be really important for maneuverability in the water. And a guy named Frank Fish, this is not a,
this is not a joke.
This is not an early morning joke. I don't do those. His name is Frank Fish. He has a company called Applied Fluids Engineering. What he did was he looked at he made a model, basically, of a flipper, airplane wing that was smooth and an airplane wing with scallops, and it's a 32% reduction in drag, which is huge. 6% increase in lift, just by putting those scallops on. So he's gotten together with a gentleman in Canada, and they started whale power, and they're using this to improve the efficiency of wind turbines as well. Very simple. This is mimicking form.
Yeah.
But these organisms, obviously over 3.8 billion years, organisms have had a little R&D time. And really, really strict criteria of success. We were talking about water and how important water is going to be. And what's interesting is that a lot of critters do not get their water from drinking fresh, groundwater. They actually get it from the air, the hot, sweaty. If you're in Atlanta in August, there's a lot of water in the air. And if you're in the fog, here, there's a lot of water in the air. So this Namibian beetle is the model for a new kind of building material, a cladding for building. Basically, what this Namibian beetle does is it's got these wing scales, and these bumps have water-loving tips and water-shedding sides. And so when fog comes in, balls of water start to build up on the tips. And then they have their wings up like this, and gravity takes over. And what you've got is a continual flow of water. You've got a water catching device. It's actually 10 times better than our fog catching nets. 'Cause we catch fog with nets. This is a picture of a water theater in Spain that is being built. And Kinetic and MIT, by the way, are making these materials. The back of it, you can imagine the back of it being clad in this material that mimics the beetle bumps. And while you're watching theater, it's gathering water for the building. Now, what's interesting is that, we're pumping water up all the time in buildings. And there's fog at the top of the building. So at the 50th floor, there's water. And this kind of a device would grab that water and let gravity take it down. So that's another example of the energy use. Of course, the sunlight, the energy for storing current sunlight. This is huge. The whole artificial photosynthesis world, I think, is going to be very important. Daniel Nocera from MIT, who does artificial photosynthesis work, says it's basically down to three game changers. Make photovoltaics cheap, replace noble metals like platinum, which are in fuel cells now, with common ones, and split water with light. This is basically this is the gizmo in a leaf that grabs the light, and this is water, and this is oxygen coming off. So the things you can already buy today, these are solar cells based on photosynthesis, dye-sensitive solar cells. Sensitized solar cells, they're called. Lots of people doing that, but the biggest one here in this country is Canarca in Massachusetts. They're thin film, much more benign than our other technologies, even the other thin film solar cells. It's titanium dioxide, basically. And they found the best dye right now is blueberry. And they're not as efficient, but they work better in low light. And then as far as fuel cells replacing platinum, this is the hydrogenase enzyme. Remember Craig was talking about the hydrogenase enzyme. This is a mimic of it. That's the thing about these enzymes. You can look at the active site of the enzyme, and if you can make a catalyst that works like that, you don't have to use the enzyme itself, nor the critter. And coating that, the platinum catalyst on a fuel cell, with that instead of platinum is a real cost saver.
Oh, yeah.
And there's so much going on in this field, and so many different labs working on it. This is John Barber. This is the splitting water to yield hydrogen piece of it. And plants are doing it all day long. You know, when you walk outside, everything we want to do in terms of fuel cells and solar energy is being done really quite well. The science is just catching up. We're just realizing what a water splitting enzyme looks like. We just took the picture of it for the first time. And now to mimic that, in other words, to have a device that can dissolve in water and through solar power, split water to make hydrogen instead of using fossil fuels for that. The materials manufacturing, the self-assembly, I think, is a really interesting piece of this, too. This is basically our recipe right now for making materials.
Right.
Heat them up, lots of pressure, lots of chemicals.
Lots of transport.
Yeah, and if you were that, caribou and you had that horn, you can't put your head in an oven to make that ceramic, to bake that ceramic. So life has really learned a completely different way to do it. Same way with this really strong spider silk. Chemistry and water and at room temp. Same way with the inside of an abalone shell. This ceramic, that's a picture of ceramic of this abalone shell, the mother of pearl, self-assembling out of seawater. And people are starting to mimic this. In other words, a new kind of manufacturing in which you put the precursors, you put the building blocks of a ceramic in a beaker with no heat underneath. And as long as they have affinities for one another, they jigsaw together into the kind of material that you want. Same way with different materials. These are the silicates, the things that make computer chips and fiber optics. Biosilification is something that is now we're able to do at the lab stage. IBM just announced a chip that is 35% faster, and what it's doing is it's able to dissipate heat and keep it from getting as hot to begin with because it self-assembles at a nanostructure. And it, as they talk about, they learned this from how the enamel on our teeth self-assembles, or how shells self-assemble. So this is and that's Johanna Eisenberg of Lucent, recently of Lucent, and Dan Morse of UCSB. So those are a few. Let's stop there. Those are a few.
That's incredible.
A few of what is now thousands and thousands of case studies in biomimicry.
So I was just at a sustainability conference, and the speaker said things are better and better, worse and worse, faster and faster.
That's good. Yeah, D. Hawk of Visa, who started Visa, said, yeah, but things are far too bad and far too long gone to be pessimistic. Yeah.
So I guess the question would be diffusion of this technology and how that's going to happen. I think that as a biologist, about exponential growth, and we're in it. What's your thinking? And maybe I'll take just a step back. for several years now, I've been trying to define sustainability as the integration or operating at the nexus of economic, ecological, and social systems. But most businesses say what? What exactly does that mean? But I think one of the exciting things about what you're doing is now we have, as Tim Brown of IDEO would say, actually a vision of what it can look like, and that becomes the design metaphor. How would you define sustainability, and how do we move toward that faster?
Yeah, Tim's point is right. When you've got existence proof that it can be done, and you've got a whole set of models, you say, we can't use that as an excuse anymore.
Yeah.
You can do this sustainably. And I have to speak as a biologist. Sustainability has to do with a success. Let's talk about let's ask what life calls success. Mm-hmm. And for an organism, success is, and we are an organism, success is keeping yourself alive long enough to have an offspring. But it's not the offspring in this generation that defines success. It's the offspring, it's your genetic material 10,000 generations from now and beyond. Success is how much of your genetic material gets carried on throughout time. And you can't take care of your offspring 10,000 generations from now. So what they've figured out how to do, and this is the key to their sustainability, is to take care of the place that's going to take care of their offspring in the future. And so what life has learned to do, all these adaptations, if you put them in ensemble, life has learned to create conditions conducive to life.
Yeah.
So you're a tree, and you wind up building soil. You wind up filtering water. You produce air that other organisms can breathe. It's all part of the system. Mm-hmm. And that's a huge design brief for us to create conditions conducive to life.
So if I'm a business and I would be interested in developing this as a part of our innovation practice, what's the next step?
It's interesting. It's a whole new field. When I wrote the book in '97, the phone started to ring, and it was companies like Interface and General Electric and Herman Miller and Kohler and Kraft and Nike and Patagonia, you name it, every industry. Mm-hmm. And what they wanted was to do biologically inspired design, but they didn't know any biologists.
Right.
So we started a company called Biomimicry Guild, which is a group of consulting biologists. And we go in and we work with engineers, and it's called biologist at the design table. That's the new career path, really. And what we do is, say you're making a desalination plant. We'll go in and you'll ask us, how does nature recover fresh water from salt water? Mm-hmm. So we'll say, okay, we'll talk about mangrove roots, and we'll talk about the nasal glands of seabirds, and we'll talk about your own kidney, and give you sort of a taxonomy, amoeba through zebra, of how life has managed to do that separation. And what that taxonomy gives you is, a couple of dozen ideas that are well worked out, physical blueprints that you may not have thought of.
Yeah.
That's how we work with people now.
So the focus, we'll just shift for a minute to 3 to 5 years out. What do you see happening? What's needed? What needs to be done, and what will be happening in that time frame?
Wow. I think a lot of the enabling technologies are going to be much more on board, and by that I mean, well, for instance, that's the self-assembly work. As we get the recipes for what to put in that beaker to have self-assemble into a three-dimensional building material or whatever, or any product, and at the same time you have the 3D printing and fabbing that's going on. You're going to be able to put those liquids into inkjet heads, in a sense. And you're going to be able to put life's architecture into a CAD program. And you're going to be able to basically layer by layer create three-dimensional objects that do have the intelligent shapes that you see in the natural world and have the intelligent architectures. I think that's really something that I'm watching. The other thing I'm excited about is the whole realm of green chemistry, in which we're looking at the industrial chemistry recipe book and saying, okay, look at the family of reactions. How would nature do oxidation reactions? How would nature do reductions? And literally, hopefully, replacing the industrial chemistry book with nature's chemistry. What's needed is, this is really, it's not even, while I want more biological research, and I think it's important, it's not even a matter of having that. It's literally an information problem. There are tons of biological papers that are sitting gathering dust. People, designers and engineers, need to have access to that information at the moment they're creating in the way that they need it. So one of the things we're working on, and we really need help from the IT community. Every time I come to California, I say, come and help us, because we're not IT people. We're trying to create a portal that, a Google of nature's solutions. It will organize all biological literature, which is a big task, by function. Because right now it's not organized by function. You don't if you are trying to find a better way, a lubricant for engines, your best recipe might be a slug. But the biologist is publishing that paper and never uses the word lubricant for what the slug is traveling on. It's a different set of language. So we need to somehow build the Rosetta Stone between those. And then to serve up the biological information in a way that engineers and designers can grab a hold of. Very visual, kind of cherry pick the best ideas for them and serve it up for them. We're thinking of calling it Biomuse. And that's a tool, a web-based tool, and it will be open source. Eventually, our dream is to have, we'll put up enough biological information that people will get a feel for it, that industries will start coming and posting challenges, for instance.
It's exciting.
And then biologists, having heard of this, I was just at San Diego Zoo with Paula Brock there, biologists, having heard of this, will think of this as a place to publish their work.
Wonderful. Well, thank you so much. It's very, very exciting. I'm very hopeful.
Thanks, Cynthia.